and inverse functions. This is in section 3.5 of your algebra textbook. We're going to start by talking about one-to-one. Remember, when we were talking about a one-to-one function, it means that every y value has, one more time. Is the image of at most one x value. And I can think about this as a Venn diagram. So I can't have, I have two sets here. I can't have more than one arrow going into the same value. This would be one-to-one. This would not be. At most one arrow in. This is going to become important as we discuss inverse functions. So, with that in mind, I'd like to determine whether this is a one-to-one function algebraically. If it's one-to-one, I know that if I have two equal y values, then I must have the exact same x values as my input. So I'm going to test this way by looking at f of x of 1, f of x of 1, and I'm going to say it's equal to f of x of 2. And if I find, after I do some algebra, that that means that x1 must be equal to x2, then I'm going to know that it's a one-to-one function. If, on the other hand, I get two different values for x1, then I'm going to conclude that it is not one-to-one. Now, in thinking about this, I know what this graph should look like. This graph is going to be an absolute value graph, and it's going to be shifted down. Everyone look at the picture and try to decide if you think that that's one-to-one. We'll figure that out in just a minute, and I'll talk about why I can tell by the graph it is not. So, if I look at this and substitute x, the absolute value of x of 1 plus 1, and set that equal to the absolute value of x of 2 plus 1, I know that x of 1 plus 1 has to be equal to x of 2 plus 1, or x1 plus 1 has to be equal to the opposite of x2 plus x1, which is going to be minus x2 minus 1. I solved each of these for x1, and I found in the first case that x1 is indeed equal to x2. However, in the second case, I find that x1 is equal to the opposite of x2 minus 2. Therefore, if it is not one-to-one, if f of x1 equals f of x2, then it's not necessarily true that x1 equals x2. Now, let's look at another example. Here's another one. Write this function down. F of x equals 5x to the third minus 2. We're going to check this one algebraically as well. So I wrote out f of x1 equals 5x of 1 to the third power minus 2. F of x2 equals 5x to the third power minus 2. And I set them equal because if I can show that I know that my y values are equal, if that implies that my x values must have been equal, then I know that it has to be one-to-one. So if f of x1 equals f of x2, then x1 equals x2, therefore I know it's 1 to 1. So you can see as I solve this, I add 2 to both sides, divide both sides by 5, I find x1 must equal x2, and therefore it is 1 to 1. Now, before we move on, I want to go back a minute to this graphical idea. I know that we've talked about it before, but think to yourself for a minute how you can tell from a graph whether or not it's 1 to 1. And there is a line test. Did you guess it? It's the horizontal line test. If I can draw a horizontal line and it intersects more than one spot, I know that it's not 1 to 1. Now, next we need to talk about inverse functions. Remember, inverse functions undo each other. So, if f and g are one-to-one functions, such that f of g of x equals x for all x in the domain of g, and g of f of x equals x for all the x in the domain of f, then g is the inverse of f. The function g is denoted by f to the negative 1, meaning inverse of f. And you can see in both of these composite examples, f undoes g, and g undoes f. You get back exactly what you put in. That's what makes an inverse function an inverse. You get the identity back. So, we need to also talk about the domain and the range of inverse functions. So here's an example for f of x equals 5x. The domain of f has to be equal to the range of the inverse, and the range of f has to be equal to the domain of the inverse. And you can see that through this example. If you put in x for f, this is my domain, and it's actually all reals are in my domain, and I apply f, I'm going to get out 5x. And again, this is going to be all reals. Then, working backwards, if I start with my all reals, 5x, and I work backwards, I'm going to get x back. And that is still all reals. So in this example, the domain and the range of f are both all reals. And the domain and the range of f inverse is again all reals. And we'll see cases where we have something other than all matching in a little bit. Oops, I added a page, didn't want to do that. Okay, so I really pretty much already gave this away, but if I look at this, if I have the inverse of f and composed with f of x, and then I reverse the order, an inverse undoes the other. So, if I put x in, I should get x out. That's what makes the functions inverses of each other. Graphically, inverse functions are symmetric to what, do you think? You guessed it. It's my line. Ooh, not drawn so well. It's symmetric to my line y equals x. Not all functions have inverses. I want you to consider a parabola. If I take my parabola, f of x equals x squared, and I reflect it over my line y equals x, you'll notice that this is my reflection. This is a relation, but it is not an inverse. An inverse is a function. So this is not an inverse. The inverse is a function. Now, what test would tell us if the function has an inverse? Well, in order to have an inverse, you have to be 1 to 1. So, the test that would tell me would be the horizontal line test. If a function passes the horizontal line test, then it has an inverse. So we've talked about everything an inverse has to do. So let's see if we can find an inverse algebraically. Now you know f of x is really y. This is y equals the square root of x plus 2. Now I want to find the inverse of f. Remember, when I find the inverse, I am switching my x's and y's. So switch x for y and solve for y. We're going to square both sides. And that gives me y plus 2. And then we will subtract 2 from both sides. So now I have x squared minus 2 is equal to y, and that is my inverse function. And I'm going to use the correct notation. Now, does anyone see a problem? This function here, if I was looking at it just from scratch, I would say the domain was from negative infinity to infinity, and the range was from negative 2 to positive infinity. And remember, the range of my function has to match the domain of my inverse. And the domain of my function has to match the range of my inverse. So I got to set it up so it works that way. Now, if you look at this example, square root of x plus 2, if I figure out what the domain is of f, I would say that x plus 2 has to be greater than or equal to 0. Solving for x has to be greater than or equal to negative 2. So my domain is from negative 2 to infinity. The range is actually harder. I don't like how that infinity symbol turned out. Let's try it again. There we go, that's better. The range is harder. From the range, I have to picture what is going to happen with my y values. And if I were to graph something like this, remember it's absolute value. My parent function looks like that. And remember what the 2 does. The 2 here is going to cause my graph to shift to the left. So it's going to shift to the left 2. That doesn't really do anything with my range, but we really do need to picture what that's going to look like. So my range is from 0, that's all the possible values of y, to positive infinity. Now that I have my domain and my range, I have to make sure that it matches. So my range of my function has to be the domain of my inverse. The domain of my inverse is from 0 to infinity. And the range has to match the domain, negative 2 to infinity. I hope that makes sense. Oh, and I have that drawn out for us. How nice. Why don't you give this one a try? I want you to find the inverse function and the range of g. Pause your video. This should be the inverse function, but I am actually going to check it because I have this feeling I disagree with it. And if I do, I will post a revision to this last example. So you're going to change your, actually, let's just do it and I'll take care of it. Let's see. I'm going to copy this over and I want to find the inverse function. So let's give this a shot. I'm going to change my x's and y's. And I'm going to solve for y. So we're going to subtract 1 from both sides. And then we're going to square both sides. When I square both sides, I get x squared minus 2x plus 1 equals 2 plus y. Then I'm going to subtract 2 from both sides. This is my inverse function. See, I knew I didn't agree with it. There. That's my inverse function. Now let's think about the domain and the range of the inverse function. Well, let's see. Of g, my domain has to allow 2 plus x to be greater than or equal to 0. So that means x has to be greater than or equal to negative 2. So my domain here is from negative 2 to positive infinity. Now, my range, again, the range is harder because I've got to picture my graph. This is my absolute value graph. The first thing that happens is it's reflected over my x-axis. So now it's down here. And then it's shifted up 1 and left 2. So it's going to be over here. The important point for the range is right here. It's shifted up 2. So my range is going to go from negative infinity to up to positive 2. Now, the range and the domain of my inverse are flipped. The domain of my inverse function has to be from negative infinity to 2. And the range of my inverse function has to be from negative 2 to positive infinity. So let's see, what did I agree with? I can't get this to work. I did not agree with my inverse function. Did I agree with my domain and my range? Nope, didn't agree with that either. Darn it. Anyway, this should be your answer. Now, the next thing I want you to do is I want you to work on your homework. That wasn't it. Work on the homework that's in Schoology. Have a nice day.